When we're carrying out a statistical test, we start with a null and an alternative hypothesis. The null we denote as H0, the alternative we often denote as HA. For example, we might be interested in testing whether or not the expected value of x is equal to 0 against the alternative that the expected value of x is non-zero. Now, having written down our null and alternative hypothesis, we might collect some data and get an estimate of that population parameter. So, for instance, we might calculate the sample mean is equal to 12 based on 100 observations of x. Now, the question that we need to ask is it likely to obtain a sample mean equal to 12 if our null hypothesis is true? Now, this is probably easiest to consider when we're considering a standard normally distributed variable. So if we've got z is distributed normally with expectation 0 and variance 1, then we can think about what an unlikely event would be for this standard normal variable. In statistics, economists particularly will often use one of three definitions of a rare event. It might be an event that occurs 10% or less of the time, an event that occurs 5% or less of the time, or an event that occurs 1% or less of the time. Now, the most unlikely set of outcomes are the ones that appear within the tails of the distribution. So we could think of the tails as being both the left and the right-hand tails, and we define unlikely events as ones that lie within these tails of the distribution. So if we were defining a rare event as one that occurs less than 10% of the time, we'd expect 10% of the outcomes to lie within these tails. More generally, if we define a rare event as one that occurs k% of the time, because the outcomes are split between the two tails, k over 2% of the outcomes would lie in the left-hand tail, and k over 2% would lie in the right-hand tail. So, for example, if we're defining a rare event as one that occurs 1% of the time, then the total amount contained within the two tails would be 1%, and the amount in the left-hand tail would be 0.5%, and the amount in the right-hand tail would also be 0.5%. Now, we can calculate these probabilities using Microsoft Excel, and we can use the formula equals norm.s.inv. The S is indicating that we're appealing to a standard normal distribution. The inv indicates we're looking at the inverse, and if we wanted to find the value below which 0.5% of outcomes lie, we could write 0.005. That would give us the value below which we would define as a rare event. Similarly, if we wanted to know the rare events at the 5% significance level, we could use equals norm.s.inv. And again, we split that 5% in half. That would be 0.025. That's 5 divided by 100 divided by 2. Or alternatively, for 10%, that would be norm.s.inv 0.05. Now let's see how that works in Microsoft Excel. So if we wanted to find what a rare event was at the 5% significance level, remember we split that 5% in half, so we use equal norm.s.inv. The probability of lying to the left of it would be 0.025, because 0.025 represents 2.5%, and that would give us a value equal to minus 1.96. The probability of randomly observing an outcome to the left of minus 1.96 would be equal to 0.025. Looking at this diagrammatically, we can see that if we have 2.5% of outcomes in this left-hand tail, Because we've just seen that 2.5% of outcomes lie to the left of minus 1.96, we can see that that value beyond which 2.5% of outcomes lie is equal to minus 1.95996, or rounded to 2 decimal places, minus 1.96. Now the normal distribution is symmetric, so if we were to plot plus 1.96, then we would know that 2.5% of outcomes would lie in that right-hand tail to the right of plus 1.96. So the probability of randomly observing an outcome from a standard normal distribution less than or equal to minus 1.96, that's going to be equal to 0.025 or 2.5%. Similarly, the probability of randomly observing an outcome greater than or equal to plus 1.96 is going to be equal to 0.025 as well, and the probability of seeing an outcome either greater than plus 1.96 or less than minus 1.96, we just add up those probabilities and the total shaded area here is equal to 5%. In this video, we've seen how we can find the most extreme k% of outcomes within the normal distribution. If we wanted to find the most extreme 5%, for instance, we could use the formula equals norm.s.inv and then in brackets 5% over 2 or 0.025.